We had a lot of questionable leads at times during class.
Yes, and Drake, you put down, make sure you're in AC/DC mode. That's correct too. Yeah, questionable leads. That is a big issue because a lot of people think, well, a small strand's not going to hurt me. Yeah, right. How many times I've been nicked because I would check my leads in the beginning, and then something happens where I actually nick the lead, and then the exposed conductors come out, and it's just a small one. Oh, it hurts. It hurts. And you cannot repair a DMM lead if you don't splice them. You can repair the ends, but if it's broken in the middle, no, just get someone to do set leads. Get someone to do set leads. So good, excellent. Everybody's doing good on that. Okay. All right. This book right here, measure voltage source. Which one is that one? Is that which letter on those pictures is measuring the voltage source? In case you guys don't have the book. Okay, we got a couple D's. All right. Okay, that's good. Measure the power supply output. Okay, good, Jeff. AA. Yes, and also remember that even on power supply, on your power supplies, you don't have to have a resistor. Remember, on our power supplies, all you have is 2 leads coming out. So just keep that in mind, that RL, that are load, it could be like 2 open connectors, a ground and a positive and a ground, right? Could be those 2. By the way, the first thing I would check if I ever open up a power supply, before, let's say it doesn't work, the lights doesn't even turn on. I checked the fuse is good, but nothing's turning on. Got some little crazy smell, but I open it up. Where do you think I'm gonna look? What's the first spot you want to look at? Do you want to look at the output? Do you want to look at the input? Okay, we can look at the input. Okay. All right. Power light goes on. Nothing's really wrong. Okay, I get that. Okay. Okay, input. I look at, to be honest with you, I break it into what I call segments. I do start with the input side, but I assume that the input side consists of pretty much a transformer. Not too likely that my transformer would go out unless you really beat on the thing. I mean, the transformers are meant to take a lot of abuse. If it's supposed to handle 20, 30 amps, it's going to handle 20, 30 amps. So pretty much input is just a quick glance to make sure none of the wires melted, first of all. Okay, it's no wires melted. Now I'm going to break it up. I'm going to say the transformer is good at this point. I'm going to start visually, before I even put a tool in there, I'm going to visually look at that board to see if I see anything. I said I smelled something. Could be a couple of different things going on. If I have some ductors, I could have some ductors that could have cooked up on me in there too. So the first thing I'm going to look for is a discoloration. Also, I'm going to see if there's any type of, if there was any black on the frame. That is an indicator that you had an arc go on, an arc flash in there. And also, I'm going to look at all the caps. If I see any caps that are bubbling up on top, or that so they're just blowing apart, then I know something has happened to those caps. So those are the things I'm going to look at visually. So if I see anything that's the arc flash, first thing I'm going to look for in that general area is what caused that arc flash, what that arc flash came from. You'd be surprised how many times the capacitor is blowing up and then all the parts are flying out of it, and all of a sudden it's hitting metals, hitting the board, and it's arcing all over the place. It's not taking out the input fuse. It will not take out the input fuse because it has nothing to do with the input fuse. It's taking out the main board. So at that point, I look at it and I shut down power, discharge my capacitors the correct way. And then what I want to do is make sure that I'm going to make sure that no voltage is present around there. So I'm going to unplug my unit, and then I'm going to recheck the discharge. Now I'm going to go in and I'm going to look around. When I start looking at something, I'm going to start physically being a detective and see what's going on. Did I destroy a board? Did I just lose component? Where did that black arc come from? Usually you can see on the board the traces where things have blown apart. So the biggest question that you have, okay, you turn the board upside down, you pull it out, and all of a sudden you got a trace that's totally melted, just wiped out. What do? You repair it. As long as it's not an aircraft power supply, or it's not medical, or it's not something that's going to be life altering, repair it and then retest it. But before you turn it back on, find out what blew. If those capacitors blew, put some new ones in, higher voltages, same values, but higher voltages. Just gives it a little more protection. Change all the capacitors out. Check the other components around it. If there's any transistors, make sure the transistors are working. Okay. All right.
Hey, Charles?
Yes.
Just kind of a side question here. If we had a power supply like the one that you're showing us now,
yes.
If that were plugged into its voltage source, say, an outlet in the wall, but it had no load, there was a switch before the load, so the thing's not actually running anything, it's turned off.
Sure.
Does it still draw power from the wall? It's still consuming juice even though nothing's going anywhere?
Yeah, you're talking on the secondary or the primary side of the switch. Is there a switch on the primary or secondary?
Well, let's say we put a switch right before the lead off to the load on the right-hand side.
Okay, so it's on the load side. So still, you have the transformer. That transformer is still consuming power. Even if there's no, let's say there's no switch on, you just got things plugged in, there's no switch on the primary side. You're still drawing power because your transformer.
So that's why they're talking about unplug your wall warts and other bricks. Yep. To save on your electric bill.
Yep, you're absolutely correct on that.
And how will we compute how much power is being drawn because there is no load? Or is that too much?
No, that's a good question. There's a couple ways to do it. Number one is they do sell meters that they're for $15. You can plug them in. You see what your load is with the thing totally off. You can, if you had a clamp amp meter and you know how to use it, you could get it from that way as well too.
Okay, I mean, there's ways to get it.
Yeah, you can also disconnect the fuse and use your multimeter and put it in series. Put that fuse as a 10 amp. Okay, meter's now set for 10 amps, and turn it on, and then plug it back in. Just don't touch the multimeter leads.
Okay, I was just wondering because a lot of the devices we have now, I mean, like TVs with a remote. Yeah. Well, that thing's never off. It can't be if the remote's going to work.
No.
But if you had something that truly wasn't, it was a transformer like for a computer, but it wasn't plugged into the computer, it's still drawing juice.
It is. It is absolutely drawing juice. If there's an LED on, it's drawing juice. If there's a transformer, it's drawing juice. Unless you have a switch on that secondary, on the primary side where it cuts the power totally to the device, you're drawing juice. And I'll guarantee you're not doing that because a lot of these TVs, you have what they call monostate. I think it's monostate. It's an oscillator. I'm moving my mind here, but basically, you use your remote control. You turn it on, right? Well, you need to have that circuitry live in order to be detected. So that's drawing juice.
Okay,
so in all honesty, you could draw quite a bit of power. That's why they say if everybody shuts off everything or unplugs your chargers and everything, yeah.
All right, thank you.
You're welcome. Let's see, measure the power supply fuse. Measure the power supply fuse.
Were you talking to me, Charles?
Anybody. That sounds like a person I want. Sure. Victory.
I'm going to pass on that one.
Okay. See, yes, it is. Let's see. Look at the diagram. I know these leads. I think this thing should be in color. That multimeter on the bottom left-hand side is pointing toward the fuse. So that's the power supply fuse. So, yeah. How many taps do you think there is normally on, let's say, a normal TV or any device? Is it a single transformer, or do you think it's a multiple tap transformer?
Charles, can you repeat that? You're breaking up bad on my end.
Okay, sorry.
It's not your fault. I think it might be my bandwidth, but sorry about that.
No, it's all good. On a transformer that's in, let's say, a TV or any device, could be a machine, is it going to be a single non-tap transformer, or is it going to be a multiple tap transformer?
I'm going to go with multiple.
It is. A lot of times what you want is a multiple tap transformer. That's the reason why some of these devices are expensive, is those multiple tap transformers. Number one, they're very heavy. Number two, they are very expensive to make. They're very expensive to make. So a non-tap transformer, you could pick them up for dirt cheap. Multiple tap transformer. You repair a piece of equipment, you might want to go research it from a couple different vendors to see which one gives you the best price, because they could be in the range of $20 to up to $1,000. Just depends on their application. A CNC machine that we have for those Haas's, those are multiple tap transfers. You look at the television set; those are usually the newer ones. Are usually single tap transfer, but they're doubles. Then some of them are doubles. And the reason for that is that you have, you have the low voltage 5-volt systems for your board, but you also have the audio side too, where you need to have multiple voltage levels. So, like minus 12, plus 12, minus 4, minus 12 volts, something around there. So, okay. All right, so we are done with that. By the way, if Cody comes back, tell him to get registered. I'm glad to have him stop in and see me. Have him stop in and see me. I'd like to see that guy. I miss him. Okay, so all right, so what we are going to do is I'm going to give everybody credit for the solid state study guide. I'm going to write that down in my notes. See my notes? See, got some notes here. So study guide. Anybody who's on tonight got full credit. We will be finishing up the study guide in here. There's a couple more spots in here. We have soldering, and then the triax and diax. Those are called thyristors. There's triax, diax, and all that. Yes, you do need to know those. Those are important. A lot of times, what we use is a diac, and diacs allow us to have voltage in both direction, AC voltage in both direction. So we'll use that in conjunction with an SCR and also a few. All right, I was just looking at some of the notes you guys are typing on there. All right, enough of the study guide. But if you want to do is finish up the stuff in here and send it to me, do it. Because guess what? It's going to be due. All right, I'll post up some of what's remainder of the stuff. So whatever we have left in the weeks in this book, get it done. All right.
So what are you requesting from the study guide?
So in the study guide, we have left, if I remember it, we have left is chapter 13 is triacs and diacs, and it's called thyristors. And then chapter 12. Okay, so 12 and 13 are left. I think that's it. 12 and 13, and I think 4 soldering. That's it. 4, 12, and 13. I think that's it. That's it. Yeah, we're done. Photonics, don't worry about photonics on it. We'll do that together in class.
So Charles, do we have assignments out here for those chapters yet?
Let me check. Good question. Let me get off of this and let me check. Okay.
Are you answering?
Number 1.
Okay, so the question
on
is
the Word document. On the Word document.
Okay, because I see the 7805 and B.
Yeah,
Oh,
this
wait.
one says this Word document should say voltage regulator questions. What is the dropout voltage for a voltage regulator?
Okay, I got it.
And that is the voltage that you need to be, it's the minimum voltage for the regulator to start activating. So the second question I have for you, and this is not on that sheet, is what are most of those regulators made up of? What kind of component what's the majority of the component in those regulators? Is it diodes, transistors, capacitors? What is the majority component?
This would be diodes.
Okay, diodes close. There's probably there's something more bigger than that. Yes, it is transistors. That's why a lot of
is it referenced inside of one of our books that maybe we can turn to and be more, have more information?
Well, I would say yes. Hold on, I take that back. Yes, it is. If you actually do electronics principles and applications and you look at that book under chapter 15, let's see if it does, it covers it. Maybe it's not under chapter 15. No, they don't get into the interworkings of the chip. This is information I'm trying to just to feed you back, okay? Just give you some information on this. Majority of those chips are all transistor based. That's MOSFET based. And that's how we switch things on and off. So in those chips is what we call feedback. So when the chip sees a voltage on the output, it's feeding back the voltage to the input saying, okay, we need a little bit more. So that's where that plus 2 volts is to what we call activation voltage. I thought for sure it was under chapter 15, but it's not. Okay. Why do we want to have thermal shutdown in chips? So right now we're under, this is actually under your electronics principle applications book. This is chapter 15 called regulated power supplies. This is called regulated power supplies. So I'm just giving you information. We're going through that book, that chapter, which covers the 7805 to 7812 with Zeners. It also gets you into switching power supplies. That's where we're at. So I'm using that as a reference to everything we're doing. So just right now. Yeah, that's something that's important is some chips, majority of the chips that are regulator chips, and that could be those ones that look like this. And they also have ones that are IC based, and they have like an 8-pin or a 6-8. It could be an 8-pin, it could be a 16-pin, it could be a 14-pin chip. It could be any of those. You want protection, and a lot of times there'll be just a thermal sensing device in there, a little thermistor that actually senses it, and it'll actually open up and it'll shut it off. And then yeah, you're protecting it because those chips are expensive. In fact, see if the book has some of that stuff. 7812, 7812. I'm looking to see what part of the book has just a little bit here on it. They talk a lot about, oh, there it is, a 723 chip. That's actually a 14-pin chip. That's a regulator chip. And that has current limiting too. So we could actually do is we could have voltage regulating, we have current limiting, and we have thermal protection. Just imagine if your chip, this guy, for example, and you wanted to put in some current limiting on here, right? What's the reason for heat? Current. Before we even get to even the thermal port of this chip, we can put a current limiting on this device. Let's see. I'm just looking to see if there's anything else. All right. All right. Let's. Any other questions about in regards to thermal protection or dropout voltage? Okay. Second question, what is the minimum voltage for the following voltage regulators? What's if you have a 7805, what about what's the minimum voltage that you need to run it? That's what that question is asking. So yeah, 7805, what's the minimum voltage to make it out?
Volts?
What's that?
Is it 7 volts?
It is 7 volts. Yes, it is. How about 7812? What is the minimum? What's the the minimum voltage to operate a 7812?
Is it 12?
Not 12.
Is it 5?
What's that?
5?
No, for the 7812. So the 78. First of all, how much voltage are we running? Yes, Drake, that is correct. What is the minimum? What is 7812? What is that type of regulator? How much voltage is that regulating?
I guess 12 volts plus 2, right?
Yeah, 12 volts plus 2, so you need 14 volts on that. Yes. So. Okay. So the minimum voltage on these, number one, for the 7805 is 7 volts to get a 5 volts out. And that's even pushing it. A lot of times what we'll do is for, like when I design power supplies, I always go with, if it's 7805, I go to 10 volts on my supply. Why? So I get more current. All right, I always give it that little bit more room to work with. And then for the 7812, I usually kick it into a 20 volt range. Again, more current. So if I try to drive something that has a higher current value, at least I know that regulator can handle it. Can my circuit handle it? That's the question. I mean, you asked me to design something to handle 2 amps. I'll give you probably 2.5, maybe 3, but I ain't giving you anything more than that.
So 2 volts is the minimum, but you may want to go to more.
Yep. And we saw this on when I was running it last week when I was doing that test. You saw it start dropping out right around the 7 volt range where it was kicking on. Yep. Never go for the minimum. It's like building your house on the minimum code. Not a good idea. All right. Wind, you don't want wind getting inside your house to heat when you're heating your house. Okay, it's going to cost you money. So, okay, let me take a look at the question here that we have here. Drake, do the last 2 numbers in the name correspond with how? Yes, it is. 7805 is 5, and 7812 is 12 volt, and then 7809 is 9 volt. And I can't remember them all, but they're out there. Usually the last 2 numbers in the 7800 series and the 7900 series. 7900, if I remember right, is your negative voltage. So keep that in mind. So yes. A lot of times what we get is we'll be changing parts out on a regulator, such as the 7805. I think it's 7805, this guy. And these things do go out. They're notoriously known to go out. 7805s are used on USB ports all the time. And it's the first chip that goes out, whether this type of package or IC type of package, whether it's service mount, it doesn't matter. They're notorious at going out. And when they do go out, a lot of times the tech, when they're fixing it, will look at the chip itself and say, okay, this is the chip we need. What they forget to look at on there is the current limiting on this thing. And then they think all 7805s are the same. They're not. You got to watch that current. So if you get the same manufacturer, then you should have the same spec. But a lot of times you're not going to get the same manufacturer. You don't have to have the same manufacturer. Such as example, National Instruments makes these chips. You don't have to buy a National Instrument chip. You don't need to buy a Mercedes when you could buy the Pinto. Just remember, the Pinto needs to be able to handle the current. Okay? All right. Okay. How about if we take a 3-minute break, and then we'll come back, and I'm going to go and just going to take care of something real quick here, and we'll get going on this, and we'll finish up for tonight. Sound good? Okay. Voltage regulator.
Is it just the device used to maintain a constant voltage?
Yeah, it's a constant voltage with feedback, right? So it's sensing the output to react to so the input will react to the output. So it's basically a feedback. So you got your output feeding back to your input. I'll draw a diagram in a minute on that. So that's what a voltage regulator is. So what is the difference between a Zener and a regular 7805? So you got a 5-volt Zener and you got a 7805. What's the difference? They both give me 5 volts. What's the difference? Anybody want to try your hand at that one question? This is one of those questions like, aha, that's why we're doing this. Okay, let me put it this way. Which one has feedback, the 7805 or the Zener? If you take the Zener, thumbs down. If you want the 7805, thumbs up. Okay. Okay. Nathan, what do you think? It's 7805. The Zener is just, it'll sense it. And remember, it reacts due to its reverse. It's called the Zener breakdown voltage. It's the reverse Zener breakdown voltage. That's the only time it starts reacting, but it doesn't really have, it's not going to be able to react as fast as the 7805. It's going to maintain the 78, it's going to maintain a 5 volt, the 5 volts, but it's not going to be able to maintain that current. It's going to be screaming, and we're limited how much current we can do with the Zener. With the 7805, if we start loading the current, that voltage is going to lock in. Think of this. The old tubes on TVs, and you see them on radios. If you have 300 volts DC, and you want to lock it in at 300 volts DC, you definitely do not want to put a Zener on there. But if you lock it in with a 300 volt regulator, and let's say you touch it, you're going to get 300 volts out, and it's going to pump out as much current as it can to you. It's not going to kill you. It's going to burn you. It might give you a little bit sting in the morning with all the burn, but that's what it will do. So just keep that in mind. All right. So a voltage regulator is a device, a semiconductor device that provides a structured voltage output at a constant rate, no matter what the current load is. The difference between a 5 volt Zener and a 7805 is the 7805 provides feedback. It provides feedback to it. And what regulators consider adjustable? Let me show. Let me do something for you before we get into that question. So let's talk about that. I'm going to share a screen here. Yes, go ahead. Yes.
You, on the last question, you talk extremely fast not to be writing notes on the board.
Okay, sorry. Okay, go ahead.
So can you repeat that answer again, please?
Number 6?
No, you haven't done 6 yet. I'm talking number 5.
5. What's the difference between a 5 volt Zener and a 5 volt regulator?
Yeah.
A 5 volt regulator, 7805, has feedback, while the Zener does not. think that gives me 5 volts. I'll find out in a second here. So what I'm doing here is I'm going to show you something. This explains the last question, and I'm just going to do something here for you. There's actually leads us into a few things we're going to be doing here in a second. So 7805, R1 and R2. And, whoops, that's not what I wanted. That's what I wanted. 2. Oops, that's not. Let's close that out. I want to delete this guy out. Get rid of him. Resistor. Much better. Okay. And what else do I need? Our load. Okay. Oh, I needed that one. Okay, I was correct. Control C, Control V. Okay, I'm going to call this our load. So I'm going to call this our load. That's RL, not R1. That's our load. And we'll get into my good stuff here in a minute. And I'm going to call this, I'm just going to give a value of 100 ohms. Might just put that like that. Okay. So there is a way to make a fixed regulator a adjustable voltage regulator. And the book does talk about this. And I'm just going to do is hopefully I designed this correct and we get some good voltages out of here. Let's see, make this 480 ohms. And let's do this one. So I'm going to do is tie everything to ground. I'm going to tie all this stuff to okay. So if I do this right, and I take my, let's see if it actually works. So if I take this, and I did not give you this, so this is something new. I just wanted to show you. So if I run this simulator, as long as ups, let me put this at 20. I'm going to put this at 40 volts DC. Let's see if we can fry out some stuff here. Okay, so basically what happens is inside this chip here, we have an output. What's inside this going on inside this chip is it's sensing the output. It's telling the input, hey, give me more. And that's through those transistors, MOSFETs, transistors that are in there. So what I've done down here, and I did this wrong. Almost did this wrong. Control X, Control V. That's better. I had this wrong. There we go. So if I use this, and I'm going to say this keeps at 1K, this voltage out here should give a 0 to 5 volts output. That's where I think this is a 5. I couldn't find my 7805 on here. It was rushing. So we'll see what kind of voltage we get out of here. So right now I got 11 volts, and looks like it's adjusting. So it's not a 5-volt regulator. But what's interesting is I could go all the way up to 17 volts. So this is a, I'm not sure which one this is. I'm going to see if I can find the 7805. Let me see if I can find the 7805 for you guys. Let's see. All right, that did not work. Let's see. I'm looking to see if I can find the voltage regulators on here. When you want a voltage regulator, you get a voltage regulator. There's a lot of them on here. Just can't find the one I want. Let's see. There it is, power. That's what I'm looking for, voltage regulator. Whoops. Let's go back. See if I can find a 7805. And I think that is, this says a 5 right here. I'm thinking that is a 5-volt regulator right there. So there's a couple of them here. We'll swap it out, see what happens here. So if I just swap it out real quick. No big deal. All right, let's run this again. Yeah, it looks like it's about mil. Okay. All right, there's 5 volts. Yeah, it didn't like that. It didn't like that one. Let's see if I have the right one in here. R2 is variable. Yeah, looks good. We got to write 40. If I adjust this thing was supposed to, DC was adjustable before, it's not adjusting now, but Control Z. I'm just going to go back to my original schematic. Control Z, Control Z, Control Z. Oh well. But you see that it was giving you a variable regulator on it before, so try that one more time. That's ground, that's ground. Well, it is giving me 5 volts, but it's definitely not giving me what I want on there. Could be the way it designed it, so just bear with me on that. I just want to make sure I'm on the right track with you guys. There it is. Do you see that? See how it's adjusting a little bit there? I see my values. My values are off on it, so. But it would adjust. It would adjust. So that's one way to do it. It's basically if you wanted to take a fixed regulator to make it a variable, you put a potentiometer on the bottom down here. That's what I wanted to show you. There's many ways to do it. So I was correct. The 7900 series is negative voltages. The 7900 is negative voltages. So, all right. Shut that down, and let's go with talk about this negative voltages first of all. All right. Before we get into the LM317, take a look at this circuit. The first question is, why do we have the diodes D1 and D? First of all, is this a full wave or half wave rectifier? Okay, good. It is a full wave rectifier. Now the second question is, will it produce a negative voltage or a positive voltage? By the way, how do we know it's a half wave rectifier or full wave rectifier? Full wave rectifier. By the way, these grounds are connected together. Jeff, how do we know this is a full wave rectifier?
Well, it's got leads coming off of both legs of the transformer,
Okay.
and it's using 2 diodes.
Right, that's the first indicator right there. It's 2 diodes, and it's a center tap transformer. The center tap, if you see the center tap right here, and this is how we usually draw it in schematics. So let me just get this red. So basically this guy right here and these guys right here are all connected together. It just saves us a lot of ink and a heartache when we're trying to put a schematic together. So FY too on that. Okay, so this is a Foid rectifier. Which way is the diode pointing? Is it gonna give me the upper peak or the lower peak for the AC? Textronics. Oh, that's Textronics. I don't think it's Textronics. There it is. Okay, it's going to give me the lower peak. That's correct. It is the lower peak. So if it's going to lower peak, if it's going to give me the lower peak, and I'm just going to move things around here just a little bit. And if I connect up, I don't know if we're going to be able to see this, but I don't got enough room over there. Okay. Yeah, it doesn't like me too. It didn't like what I did there, so just give me a second. I have the ground connected. And that gives me that part coming off of it. Okay. Set. Still didn't like what I did, but that's okay. I'll see if I can get it some other way. Okay, so that's the input voltage. That's not a problem. That's our input voltage. So if I take and I don't know if I'm going to be able to get it with this capacitor in here. I might have to disconnect. I'm going to disconnect this line right here. There we go. Okay. Okay. So I'm going to get rid of this guy. I don't know why it's giving me half. That's that guy right there. Oh, oops. No, it should be okay. Right. Yep. Don't know why it's doing. It's supposed to give me a half wave right here. And it looks, let me see if it is. Where's the ground line? Ground line's right here. Okay. So it's just giving me the lower peak right now. It's giving me that's lower. That should be a smooth line right there. Do you agree with me on that? See, that's a ground right here. Okay, that's the ground right here. And this is the lower peak. So it's flat, lower, flat, and there's the lower part. It's not the best schematic in the world there. I'm looking to see if there's anything I can do to change that. All right. But you notice that this voltage right here, and I'm going to get rid of this, and I'll hit measure, and I'll have channel 2 type voltage. There it is, max, negative 10 volts. That's negative 10. Because we're on channel 2 is, let's see, it's 5. There's 10. There's 10 max right there. It's 10 max. All right. So it gives us a negative voltage. So I'm going to hook up my capacitor back in so I could actually see this a little better. I'm going to drop this capacitor value down too. So I'm going to drop it to 400 microfarad. I just got to redesign the circuit part of the circuit back up here. Okay, now if I run it, I should get some humps here on it. Hopefully I do. There we go. There's my humps. Actually, I put it down to 1 volt per division. There it is, negative volt. See, our ground line's right here. Our ground line is right. Our ground line is right here. So anything from here down is going to be a negative voltage. Anything above it is going to be a positive voltage. Okay. So the second question is on here. By the way, do you notice that if I change the capacitor, what would happen if I change the capacitor out to a bigger cap? What happens if I go to, let's say, 1,000 microfarad? What do you think will happen to the humps? Less ripple. Okay, yep, you got it. You know that. And you can see that we still got ripple. Quite a bit ripple, too. That's a lot of ripple right there. Let me see what that's DC coupling. Oh, that's good. I'm going to put it to AC. I'm going to see what how much ripple we have. Yeah, quite a bit. Ground, DC. There's DC. Let me try let me try one more capacitor on here. Let me kick the capacitor up. I'm going to kick it up to 3,500. And you can see that what happens with the capacitor. This is the fun stuff. It's a little less each time. Let me clear the board. Keeps getting less. So what would it take to get this thing really up? Well, let me show you how we do that. Like we would do over here is put this at 3,500. And then we would do is take, and a lot of times, this is sometimes on a board, they'll actually have this ready to go. So what they'll do is they won't put a second capacitor in because it's more money. They'll do is put the first capacitor and move it up to like 4,500 microfarads. So I'll show you so a lot of times what we'll do is we'll design this thing so we'll have a second capacitor. And there's a reason why you always want to have a second capacitor. It not only helps out the circuits for stabilization too, it helps stabilize. So if this thing actually gets any noise on the end, this capacitor right here will filter that noise out. That filter will filter that out. Oops. Hold on, I just moved something, Control Z. There we go. All right, let's put this back on. We're still getting quite a bit of hump on here with 3,500. How much we add? Let me see what the auto sets. Let me see what we get on this. Oh, there it is. It just need to be auto set. So you have very little ripple down here. Let me bring this up. Let me bring this up. Just bring it up. It's still negative voltage. We're at 5 volts. And looking at the ripple, I want to see how much ripple I have. So channel 2, DC, AC ripple. I'm looking at this 200 mils. So we're at, this is 200 each line up. So that's 200. It's about 100 mils. It's about 200 mils of ripple. Not too bad. Still quite a bit, but still not bad.
Charles, a question about this. So when you zoomed in on the ripple, why was it looking more sinusoidal than what we expected with this greater slope?
Okay, excellent. So basically what we have here is I changed this DC from DC coupling to AC coupling, and this AC coupling is telling me how much AC I have on that. So when I do that, and a lot of times what we'll do is we'll change the coupling from AC to DC. And what this will tell us is how much AC we have on the other end. Whoops, went too high. So in this case, if I set this thing for 200 millivolts, that means this above here's 200 and below. So it's about 100. This is about 200 millivolts of ripple. So if we were troubleshooting this circuit, let's say we're getting customers complaining, hey, my circuit is sometimes is working, sometimes it's not working. We could look at the AC coupling. We could put the oscilloscope on the output, look at the load, and say, okay, if we put a 100 ohm load on this thing at whatever voltage, this is what I'm receiving. I've got some ripple. That could be the problem. So at that point, I could start suspecting that we have a bad capacitor or we need a bigger capacitor. So, and I keep going up capacitors here. Does that answer your question? Okay. I'm going to change this capacitor out to show you what happens if I go. I'm going to go up to 4500 because I do have a 4500 microfarad capacitor. And you notice that it should take care of that ripple totally at this point. So if I bring this guy way up, you're going to see our, and I'm going to change this out to DC. I'm going to change that out to AC. Look at that. The ripple is almost gone. I'm almost at, that's 500 mils. 500 above, that's not even close to it. What am I even at? That's small. Really got, it went tiny on us. It went tiny on us. So, all right. Take a look at the rest of this circuit here. Let me get rid of this. Let's talk about these parts here on the circuit here. What does this capacitor do? And what does this capacitor do? I just went through some of those already. What does C1 do? Is that before the Zener or after the Zener? It's before the Zener. Good. Sorry, just almost had a cough there. All right. This one is the primary filter capacitor. C1 is primary filter capacitor. This one actually takes care of any transient noise that we have on this side, any type of spiking we have due to the output. That's what the C2. C2 is mostly a backup to C1. So like I said, sometimes we won't have C2 in there, but we'll have it ready to go. We'll design the board, but it's not going to be put in. What we'll do is we'll put C1 as a higher capacitor value. So that's what those C1 and C2. So C1 is your primary filter capacitor. And a lot of times what we'll do is we will put in an inductor, right? Whoops. We'll put an inductor right in here. There'll be an inductor right in here. And what that inductor does between here is it's called a low pass filter. So it only passes low frequencies, which is what we want. We don't want any high frequency. So the problem with inductors, as with any active component, it draws current. So on this side right here is we have a Zener. Let me clear this out. So I may bring this in just so you can see what's going on here. There we go. Okay, so we got Zener diode. It's facing down. So what kind of voltage would you expect on the output? So let's find out what kind of voltage we have in the output here. Let's put this on. I'm going to do a probe, voltage probe. So I'm just going to go with a voltage probe. Okay, here we go. So if I do this and I put it on, I get negative 2.86. So this is a 2.2 volt Zener diode. Zener. Notice that the Zener is actually pointing in the reverse bias direction because we're in the, if you look at, this is going to be, these diodes are reverse, right? So this is in the reverse bias condition. So this is going to give us a negative voltage right here. That's why we got negative 2.86 volts. And you see that we still have, like I calculated, what, 200 something millivolts of ripple too. That's where the 200 millivolts of ripple is still there. If I want to get rid of it, I don't know if I'm going to be able to get any lower than that. I keep putting capacitors. That's a 6,000 microfarad capacitor. That's a pretty beefy capacitor right there, but we're still getting some voltage. But we're getting what counts as the DC voltage down here. DC voltage. Good to go? So let's see other questions they have for this on this one here. So which way is the Zener diode pointing? It's actually the reverse bias, but it's going to give us a negative. It's going to give us a negative voltage, right? It's reverse bias, but it's in. Okay, what happens when the Zener leaks? Let's do some troubleshooting. Let's see what happens when it leaks. So right now, what we have is, right now this is what we have. So let's see what happens when it leaks. Okay, I'm going to keep bringing up the leakage on it. Okay, it just didn't affect it too much. Let's change this out to, I don't know, let's give it a 10,000 ohm leakage. Not too bad. So Zener diodes really don't have too much effect on, unless I hit the wrong one. Nope, I didn't. Let's do an open and see what happens here. Look at the output, what's happened to your output. So basically what happened is our Zener diode decided to fry itself out inside, and it's poof. Now instead of getting 2 volts out, we're getting 12 volts out. Just imagine if this was a reference. If this was a reference voltage, and all of a sudden we're getting 12 volts, we just fried another circuit, right? Or We got the computer actually hanging up on us saying, hey, something's wrong, giving us an error code. Okay. I'm gonna try the, I want to try the leakage again. The leakage current should give us, try 1 megohm. Doesn't have much effect on it at all. Not much effect on it. That shouldn't give us anything on it. Woo! Well, that did affect it with the leakage. We have a real bad leakage of about 1 milliohm, and we got like 1.25 volts DC out. It's almost like a short, it's like an open. That's literally like an open. Let's open this thing up and see what happens. Okay, so opening it up, basically, just whatever voltage you're getting on the source over here. That's what you're getting over here. See, that's 12.6, that's 12.6. So if we short it, before I do that, what do you think it's going to be? Give me something. What do you think it's going to be if we short that thing out? By the way, how would you short out a Zener diode? It's in a case. How about something dropping inside of it? Something on the top accidentally gets stuck into the fins, right? All of a sudden goes right in. So you're going to get, are you going to get 12 volts out, or are you going to get 2 volts out, or are you going to get 0 volts out? What do you think? Jeff, I like how you switched out your background, by the way. Let's see what happens. Okay, it's got 12. 0. Let's look at reason why. First of all, is this a series? Is this a series or parallel circuit? So if you think it's a parallel, if you think it's a series, thumbs up. Parallel, thumbs down. Series, thumbs up. Parallel, thumbs down. All right, let me try this way. Nathan, is this a series or parallel circuit right here? Okay. Andy, can you tell me if this is a series or parallel circuit? Okay, parallel. Good. It is parallel. Thank you very much, Andy. Jeff, thank you. Parallel. It is parallel. So if we short out one thing, everything else is shorted out. Remember that in the parallel circuits back in DC? Everything, that's it, right? So go goose egg. Yeah, you just toasted. If you didn't have a fuse on this side right here, you just toasted this whole thing. You fried it. That's why a lot of times they'll do is they'll put in some fusing in here, just to prevent that from happening. So if you got a regulator right here, they'll put the fuse on this end right here, or very close to this part right here. So if it does short out, it doesn't kill everything. All right, let's, what other question do we have on this? So if the Zener leaks, if it's really low leakage, you'll actually get very little voltage out. So leakage, you'll start getting some varying voltages. You won't get your source voltage, right? You won't get your Zener voltage, right? It all depends. When it opens, you get your source voltage. Any questions in regards to the negative voltages on these guys, on this? I'm just curious to see how much amps we're drawing on this thing. I got too many windows open here. And let's get this guy, boom, boom, back to normal. Yeah. That's not too bad for a 100 ohm resistor. About 85 mils. Average is about 82. It's not bad for power. So that's how you get negative voltages. Negative voltages are used mainly in amplifier circuits. They're used in amplifiers. A lot of times we'll have a circuit like this where it'll produce both the positive voltage and the negative voltage. And then we'll have like two regulator chips, the 7800 series or the 79, or a chip that could produce both voltages. And a lot of times when you see those chips inside power supplies, well, I'll show you next week when we open it up, or the week after when we open it up. These chips basically give you the voltages and amplifier circuits. These are circuits that require amplification. They could be audio amplifiers or they could be small signal amplifiers. A lot of times we'll have an operational amplifier that will have a upper voltage and a lower voltage. So just heads up on that. Any questions on this? Any questions on nope, we're good. Okay. All right, let me clear the board here. The fun stuff begins. LM317. That's good. By the way, you should have these drawings, PDFs on your email. So just let you know. Full wave bridge. I think we just did that. Regulator LM317. Ha! Good stuff begins, folks. All right. All right, so this is the LM317. LM317 is called an adjustable regulator. It's called an adjustable regulator. And how it works is that we have a feedback resistor and a adjustable resistor. It's similar to the 7805, but the only difference is that this resistor here, R2, is needed in order to provide the feedback. And that's how we actually get to adjust the voltage on it. Okay? Just give me a second. Do you guys got this drawing? Okay. My notes. Okay, so the LM317, to get the voltage out. So basically we have a bridge rectifier, and yes, we will set this up over here and we will run it. I'm going to use 3.6 or something else. I'm probably going to use maybe go 16 volt. I might use a 16 volt Zener on my output instead of because I'll have the LM317 to be adjustable, but I want to have a Zener at the other end just to give me some more flexibility. You'll see, it'll be fun. This is the fun stuff. But I will set it up first without the Zeners or anything. We'll just do with the LM317. So 317 is very common type of voltage regulator. In fact, we use it on very inexpensive power supplies. So if you're looking at trying to build yourself a power supply has a range between 1.1 to whatever your secondary source is, your DC source right here is, it'll give it to you. If you want to go down to 0 volts, you have to add some diodes into it, and we could talk about that maybe next week. But really, 0 volts is not really needed. So I'll show you some protection circuitry we put in here, and that's just, again, to protect not only the regulator, but also our circuit itself too. So the first thing we want to do is if we want to know, we need to calculate R2. If we know what voltage we want on the output, we get R2. So we need to figure out R2. So R2 is going to be equal to R1 times V out over 1.25. Minus 1. That's how you find R2. If you were designing these circuits, that's what I did. I'm just showing you so you have an idea. Okay, how did he come up with these values? There are some of the equations. Will that be on a test? No. Not needed. Unless you want to build your own power supply with LM317, and then they go into the spec sheets and they give you all this information. Okay, they give you the value of the R2. There's even a app now where you can find the R2s. If you knew your R2 value, you could actually know how much voltage out you could get. That's more important. A lot of times we'll just put an R2 value of, let's say, 300 ohms in there or 100 ohms in there. Kick one in, happy, done with it. With that, we could say that V out, this one probably would have on the test, but this one's just 1.25 times that by 1 plus R2 over R1. So in this case, if I did this and I had it, I would do is I have my R values 240 and 1K. So I could take 1.25 I'm missing something. I might be missing something out here on this. Yeah, I think I'm missing VS. I think the VS is supposed to be out here. 1.25 times 1 plus R2 over R1. And then I do believe you have to take VS. So in this case, if I took all my values, this is a 1K, this is a 5K, that's 240. It's just figure this part out and I'll get the rest to it in a second. 1.25 times 1 plus R2 is 5K over 240. And I'm just going to go with this value for a second here. I'm going to get my calculator just to check it out. So I take 1.25 times it by parentheses 1 plus 5,000 divided into 240. Maybe it doesn't have to have it. That'll give me, actually you don't need VS. That's just skip the VS. That gives you 27.29. I'm going to make sure that it's correct. Just 1 second. I'm going to make sure I'm correct on it. Yeah, there's no VS. I'm correct. So that gives me, if I use these values, I can max out at 27.29 volts. So there's no VS. I was correct about that. So this gives us, making sure all my notes are good for you guys. So the max on this guy would be 27.29 using these values. But the problem is we have to ask ourselves, how much voltage are we putting into this thing? That's going to really be the limiting factor, right? I mean, I could get out 27.29 max on this thing. But if I only have 20 volts going into this regulator right at this point at A, I can't get 27.9 out of it. I can't get magic out of it. So just remember, this math right here is going to give us our max voltage no matter what. But the limiting factor is our voltage source in. So a lot of times on a tech, I'm going to erase some of this stuff here. Tech, what they'll be looking at is, first of all, do I have an adjustable voltage regulator? How would you find if you have an adjustable voltage regulator? What would you do? If you open a box up, you see a chips in there, what are you going to do? Anybody? Victory. What would you do to find the spec of a chip?
Well, first of all, I would look at to find the spec of a chip. Well, go on the internet, Google. Or are you talking about looking inside of the equipment itself?
Well, you look at the equipment, but you're right. You go Google it, right? You go to the PDF, right?
Right.
Yeah, it'll tell you what kind of chip it is. Is a fixed regulator or is it adjustable regulator?
Yeah.
Okay. So let's see what happens with this guy. I'm going to clear the board here. Let's see what happens with our R out. I'm curious. I want to just run this thing. We're going to build it. I'm done talking. I just want to build these things. So we'll answer the questions here in a second. By the way, C1 is your filter capacitor, and then C2 is what kind of capacitor? Give me it on your chat if you want. Backup capacitor. Yeah, okay, good. All right, so let's run this thing, see what we get. I'm going to put some probes out on the top here. Okay, so far we got 28 volts max. Let's adjust this thing. So I could press key A, it says. Should be able to get mouse. Oh. Okay, here we go. So 12 volts down to 12. Well, 10 volts will get down to 10. And I could probably drop that a little more. And the max voltage on this is going to be, looks like I had 0 on it. Nope, 28, 26, 26, 26. Okay, so we can get a little bit of adjustment on here. All right. Let's see what our power is at. $4 of power out. Let's see what happens on this. I'm curious to see what our regulator's powering up at. Yikes. You see that? So we're getting a lot of power out of here. Okay. All right, let's take a look at lost a few people in the class, by the way. We're going to build this circuit. Let's answer these questions down here real quick. So R1 is adjustable and R2 is your feedback. Not sure that was question 4 and 5. What would the voltage be at point B, at point A, if a Zener diode was inserted in the circuit? So if we put a Zener in the circuit at point A, and that's right there, that's the input. Depends on where the Zener would be. So if the Zener was at this point and regulated 16 volts, that means the max we get into here would be 16. If it's over here, no matter what we adjust this thing, we get, let's say, 5 volts. That's all we get is 5 volts. All right. So if these started leaking, what would happen to them? Just go ahead on chat and we'll build the circuit. And we'll call it for the night. So let's say C2 was leaking. What would happen to your voltage? Right now, all we have is about 1 mil. So let's see what happens. Go ahead, put it in chat or something on there that you think would happen to it. So I'm going to say C2. We're just going to do C2. Continue Windows open. So I'm going to say it is going to, let's say it opens. Caps leak. They do leak. We'll get some leakage here in a minute. But if we do it open, you notice that our voltage is now bouncing all over the place. Look at our peak-to-peak voltage. That means we have a lot of ripple. So if it opens, that's C1 or C2, you get ripple. Let's see what happens when we open. Let's say we have a leakage, because caps leak. They either open, they don't short. They open or they, or they leak. So let's say we have, I don't know, let's say 1 ohm leakage. We'll see what happens with that. Oops. Thought I selected the second one. Okay. Look what happened when we have 1 ohm leakage on it. The voltage now drops way off. Yep. More ripple. Yep. More ripple. All right. Any questions in regards to this circuit? Because I'm going to go ahead and I'll build to a pot. And I have a 1K. And I'm going to use a 220 ohm resistor for my feedback. So 2 should go back to 1. And a lot of times when you're building these circuits, they're a little harder to build. There we go. 1 has my potentiometer. Okay. I'll show you all the parts that I'm doing here in a second. I'm going to move this out of the way for now. Get this out of here. Too many things here going on. There we go. Three is input. So my input's going to be, should be this guy. And then 2 should be my output. So I'm just going to connect that. I'm just going to put a wire on my output to my output. Yeah. So I got my pot. So that's what the circuit looks like. So that's my output right there. So I'm going to connect up some wires to that. We'll see if I connect up everything correctly. We'll see if I pop at anything. Let's see, that's there, that's connected, that's connected, that's connected. There's 8 volts. And we are adjusting. I don't have a load resistor on here, so it doesn't, it's not really, well, I can put a load on. Let me put a load on it. Let me go back to, let me put a load on it. So I'm just going to put a load on it. Okay, there's a load. Okay, so I got 8 volts. And you can see that I'm adjusting all the way down to 1.4. All the way up to, and this is limiting me out at 8 volts, which probably because of my feedback resistor I used right here. That's probably what it's causing it, but I can't get it up a little higher if I wanted to. But any questions on the LM317? Just feeling my circuit here. And if I put in another resistor on here, so I have 1K, that's a 1K pot. So if I use the same equation I had before, R2 over R1, so it's I got 220 ohms divided into 1,000. Times plus 1, times that by 1.25. That didn't give me a right. R2. Yeah, R2. Oh, R2 is 1,000. Sorry, R1,000 divided into 220. Yeah, plus 1 times by 1.25. I should get about 8. Yeah, about 6.93. 6.93 volts, close to 8 volts on this thing with the values I selected. Not bad. If I wanted to go higher, I could actually put different values in. I could put a 10K pot in. So if let's say I put a 5 or a 10K pot in, that means I could get that out of it. 58 volts. Pretty good. I don't think I got any 10Ks. I'm gonna check. I think I only got 1,000. Checking to see what kind of pots I got around here. I got 1,000. That's all I have. All right. All right. Is there any questions